Welcome. Thank you for having me. My name is Barron. I'm a cloud engineer at Development Seed, and I work on some open source Python tooling that I'll be talking about today for visualization and analysis. So massive amount of content to get through. And since this is a Python conference, I figure I should start with JavaScript. Talking about how you render vector data in web maps that then we can connect back to Python. So in web maps, there's 3 different steps that you have to handle to get the data to actually render to screen. You have to load the data somehow into the browser, manage it in JavaScript in memory, and render it to the screen. So historically, if you've used libraries like IPyLeaflet to connect to the Leaflet JavaScript library, it tackles these 3 parts by using GeoJSON JavaScript objects in memory, and then Leaflet to render to screen. Each of these parts are really slow. GeoJSON has a really big file size, which means that it's really slow to move data from Python into JavaScript. It has a lot of overhead just to parse that GeoJSON string into JavaScript objects, and then you have to render each of those geometries individually into the HTML canvas element, which is also really slow. We can do a lot better than this by using some of these latest technologies. So I'm using GeoParquet to move data from Python into JavaScript, which is really efficient at compression, which means that instead of maybe a 700 megabyte GeoJSON file, a GeoParquet file might be like 40 or 50 megabytes. We can use GeoArrow on the JavaScript side, which means that we're never parsing something into JavaScript objects. All of our geometries stay in binary form the entire time. And then we can use a GPU accelerated mapping library called DecGL to really efficiently copy the data straight from its binary form in JavaScript onto the GPU to be rendered. And so now connecting this back to Python, all of those steps were just in JavaScript, but then this library called Lonboard connects this to Python and GeoPandas as well. So here, this is an example of taking a GeoPandas geodata frame that has 3 million points and rendering that from the GeoPandas geodata frame into DecGL in Jupyter in under 3 seconds. This includes every single point that you see has a different color and a different radius. Here, this data set is internet speeds. And so all of that happens in this 3 seconds. And to be clear, this map is interactive. So when I render this, you can zoom in and you can get a tooltip with whatever attributes are in your data over every single one of those points. So to compare this data set, I tried this in IPyLeaflet, took 3.5 minutes and then crashed the notebook. In PyDec, which is a previous way of connecting to DecGL, it took 2.5 minutes and then crashed the notebook. And in Lonboard, it took under 3 seconds. And so how is this so fast? This connects to GeoPandas and uses GeoParquet to really efficiently move this data from GeoPandas into the browser. It uses, it parses the Parquet natively in WebAssembly on the JavaScript side, and then uses GeoArrow to directly copy from DecGL into the GPU for rendering. And so all of these steps happen like 5 times faster than just saving to GeoJSON from GeoPandas. I want to talk a little bit more about some different features that there are in this library. The architecture of this widget is such that it only sends the data itself once. So you can visualize the data first, and then say you want to explore different attributes for data-driven visualization. You can send here just the new colors that you want to render. And so this doesn't render all of the geometries from scratch. If you want to update just the radius or just the colors, you can do just that. We can also do GPU-based data filtering, where here this is sending air quality data from Houston into the GPU, and then we connect these slider elements from Python, where this is, I think, like 4 or 5 million points. I don't remember exactly. But this is passing just the range to filter into the GPU, and so that happens at like 60 frames per second. There's a bunch of examples in this documentation. The documentation you can access from ds.io/Lonboard at that link at the top. This is using Overture dataset, which is a big distribution from OpenStreetMap that we can fetch GeoParquet directly from cloud storage really efficiently, and then pass that into Lonboard to visualize this data, where each of these buildings is rendered with a different color based on its height. There's also a CLI actually as part of this, where if you have any GDAL readable file, you can pass a path to that on your file system. It'll load that with the newest pyogrio and arrow support, pass that straight. It never actually goes into GeoPandas. It uses the arrow and GeoArrow support of Lonboard, where this is taking a decently large shapefile, and in like a second, it's there where you can explore your data, see the different attributes of features. There's also a couple things that I'm working on, especially movement data. This is not yet merged yet, but this is ship data, AIS data from the US, where we can actually see an animation of ferries and ships moving around the waters on the Northeast. This is like 500,000 ships, each with some amount of trajectory information. It's not super pretty, but it could be made prettier. And so I'm trying to talk both about the visualization and about the analysis size in this talk, but the thread that really connects both of these is this new technology called GeoArrow. And the core idea that I want to get at here is that data protocols really enable innovation. And so what is a data protocol? In Python, we've actually had a geospatial data protocol for quite a while. This geo interface specification, which was created by Sean Gillies and a bunch of other people, was stable as of over 12 years ago, I guess. And just having this geo interface accessor on any object means that you can call that and get GeoJSON. And so it's really amazing because so many of these different libraries can just work together because they can see that any object has a geo interface attribute without having to know anything else about that library. The GeoPandas can work with GDAL and Lonboard and MapNIC by deciding on this interface. So why do we need anything other than GeoInterface if that already exists? Well, there's some complexities with having to go through GeoJSON, especially because the format of how you're moving the data between libraries is quite different from the optimized way that libraries store that data under the hood. And so this is an example of just calling GeoInterface on this 3 million point data set. And this takes about a minute for this just to convert all of the GeoPandas attributes into GeoJSON. And then any library that wants to consume that data has to convert it back into some other representation. And so the key problem is that calling this attribute triggers some data transformation. It's still going, okay. So really what I care about are fast data protocols that if we have, that the GeoInterface protocol is really powerful, but it could be even more powerful if it were able to share that data without a lot of overhead. And so going into a bit of history here, there's been efficient data protocols in Python for quite a while for different aspects of different types of data. This really started in 2006 with a Python buffer protocol, where they had this problem where it was really expensive to copy and convert array data, multidimensional array data, between different compiled Python libraries, like NumPy and SciPy, or whatever versions of those existed back in 2006. But the Python buffer protocol really enabled a ton of innovation by letting these libraries share data efficiently without having to have specific knowledge of each other. And so Jake Vanderplas, who is has done a lot of work in a lot of different scientific Python areas, has this amazing quote that it is really the buffer protocol and NumPy that make Python useful as a scientific computing platform, because it allows Python to be this glue language, but still be efficient between all of these different compiled libraries. And so after NumPy, we had pandas and other tabular data sources that had similar problems where people wanted to use both Python and R, or Python and some other databases or some other programs in Python, where we had the same expensive copy and convert step. And so Arrow came along as a language-independent format that could be implemented across languages and be used by multiple different projects, that then makes it free to share this data between different implementations. And so, for example, this is a great blog post on passing Arrow data between Python and R, where it used to be a corresponding time compared to the amount of data, O1 or ON. And with an arrow table on the right-hand side of this graph, no matter how big your data set is, it's always virtually instant to share that data between Python and R. And so on top of Arrow, we have GeoArrow that is this new specification that a bunch of us have been working on for the past couple years, where we have a similar problem as Arrow had before us, that we have all of these different geospatial systems, file formats like GeoParquet and other things that GDAL can read. We have GeoPandas and Python, QGIS. We have all of these different libraries. And so GeoArrow tries to solve this problem as well by being a binary data protocol for geospatial specific tabular data. And then the last part of the puzzle to bring this back into Python is to have these specific methods that allow us to share data between Arrow-based Python packages that don't have to have any knowledge of each other. So this is a little bit technical. I think Joris might talk about this tomorrow in his GeoArrow talk as well. But an example to drive this home, that historically, to write from GeoPandas through GDAL, GeoPandas would iterate over the GeoJSON features of each row in your table. So it would take its own binary representation, convert it into GeoJSON, pass the GeoJSON to GDAL, which would then parse it back into binary, and then GDAL would write that binary to the output file. But GDAL, since version 3.6, has added GeoArrow support directly, which can make this a lot faster. So when GDAL added this, they did their own benchmarks, comparing how fast it was to read into GeoPandas using this new Arrow support versus the old way through Fiona. And so with all of these file formats, it's 20 to 30 times faster to read this data from a GDAL-supported data source into a Python geodata frame than it would have been by iterating over those features and having that really expensive binary to text to binary conversion. These are reading benchmarks, but writing should also be quite a bit faster. And this brings me all the way full circle to some other work that I've been doing to support GeoArrow in Python. And so I've been working on this library called geoarrow-rust that is, the core is built in Rust, but it has Python bindings so that Python users can access its functionality without having to know any Rust. This has both file format readers and writers so that you can read GeoParquet, flat GeoBuff, GeoJSON, but also has algorithms, a growing number of algorithms to try and be corresponding with GeoPandas and other things that Shapely implements. But the core feature here is that because this is implemented on top of the GeoArrow format, we have really fast interoperability with GeoPandas, with DuckDB Spatial, with GDAL and pyogrio, with a lot of these different libraries. And so this is a relatively early project, but it has a lot of potential. All of the algorithms are like multi-threaded by default because it'll multi-thread over the internal chunks of the arrow table. And it doesn't have any dependencies. It's a single Rust binary, which means that it's really easy to install without having to worry about GDAL or GEOS or some of these other libraries. And then to clarify, the GeoArrow format is pretty stable, but the API of this specific library is not super stable yet. So use at your own risk. And some examples to show how this ecosystem works together, where reading a GeoParquet file from Rust and then passing that into Lonboard is able to take less than 2 seconds, where GeoArrow-rust and Lonboard can share the description of all of these geometries without having to do any copy whatsoever. Lonboard is able to look at the data that Rust is producing and send that directly to the browser. Since GDAL and pyogrio have added support as well, we can do whatever sequence of operations we want to between GDAL and pyogrio and Rust and pyarrow, the existing C++ implementation that has bindings to Python. And so here, this code segment is reading via pyogrio and then passing to Rust and then passing back to pyarrow. And that takes 600 milliseconds, which is entirely in the reading the zip shapefile. And then to go back to this original example where it took a minute to convert that GeoPandas geodata frame into the geointerface representation, if I access this as an arrow table between Python and Rust, this took 290 microseconds. And so it's 185,000 times faster than the geointerface for this data set, even when you take into account the fact that the initial example only produced the GeoJSON and nothing was consuming it on the other side. I have a bunch of links to examples. I've done a couple of podcasts recently that you should be able to Google. Yours is GeoArrow talk tomorrow. I would highly recommend. Will be really interesting. The geoarrow.org website and GeoArrow-RS has some more documentation. ds.io, we have a couple blog posts on Lonboard and how it works. And ds.io/Lonboard is the documentation. I have a couple minutes, so I'll go into a demo. Should I make this a little larger? Okay. So this is the example that we had starting. This is points that represent internet speeds across the world. To be clear, I tend to use points because I have this data set, but Lonboard has a bunch of different layer types. And so if we look at these layers, we can render raster data, we can render polygons, we can render paths, all of these different core geospatial data types we can render, as well as some others like a heat map layer and more data types going forward. So here, I'll skip over, this notebook is part of the Lonboard documentation and part of the repository, so you can run this notebook yourself. Here we're loading this geodata frame into memory. This has a download speed in kilobytes per second and point geometries and has 3.2 million rows. Here, I'll call this from GeoPandas method to create the layer and then create this map and just display this map. Inside Jupyter, this renders as a HTML JavaScript object inside the notebook. This renders all of these data points to the screen. Now, like, black is kind of boring. Having black points doesn't really tell you anything about the data, but we can use the reactivity of the layer and map objects to update the map. And so here, in this one line of code, we can instantly convert all of our points into blue. Still, blue is kind of boring, doesn't really tell you anything. So let's compute a linear statistic for this download speed. If we look at download speeds between 5,000 kilobits per second and 50,000 kilobits per second, we can get this normalized download speed, where 0 corresponds to 5,000 kilobits and 1 corresponds to 50,000. And we can use this apply continuous color map helper to set that onto the get fill color attribute. And now when we zoom in, we see that all of these different points have a different color that is corresponding to the color map that we assigned onto our data. And in that last cell, we can also set a different radius for every point. And so here, the points that have faster internet speeds, I mean, I guess let's go into Switzerland. Let's find Basel. Here, yeah, maybe this is the campus here that has a really fast internet speed. And then some towns further away have slower internet speeds. I'll do one quick example and then I'll go to questions. Here, this, oh, oops. I reinstalled my environment right before this demo. I want to point out that if you're using Jupyter Lab, you can use this awesome, I think I have to reload the page. Yeah, because I didn't install that package before I loaded Jupyter. Yeah, so here, you can use Jupyter alongside, you can view the map alongside your notebook. And so here, this is parking tickets in Chicago, where we can similarly go through and apply a different color map to all of our points, but have this kind of exploratory data analysis nice view where you can work with your code on the left-hand side of your screen and still explore your data on the right-hand side of the screen. This example is also in the documentation. You can refer to that for more information. Any questions? Yeah. Well, wait for the mic.
So first of all, thank you, Carl, for this very interesting talk.
Thank you.
Thanks. We've been doing similar things with data shader, and I was wondering if you can produce like an interactive legend where you actually can see the values then on the map, like an interactive legend when you zoom in, that the legend also changes. Sort of thing.
I'd encourage you to open an issue. So there's a bunch of this sort of interactivity between Python and JavaScript and back to Python that's really exciting to explore. Like, for example, if we click on one of these values on the Python side, then if we do like layer.selected index, we can access the index that we clicked on. And so you can do like gdf.iloc layer.selected index and access the row of data back in Python that you clicked on in JavaScript. And so we could potentially do something like interactive legends where based on the viewport of your data, you see the distribution of your data that updates back in Python. Right now it's possible, but you kind of have to like wire that up yourself. It's not something default in Lonboard itself.
More questions in the audience?
Yeah, so I missed the very beginning part of the tutorial stuff.
Yeah.
So may I know the backend for the front end? The map rendering is really fast, so I'm really interested in the backend for that. And also, I'm not sure if you have some like technologies to handle the overlapped points and the line strings. So, for example, if you use some backend like a leaflet,
Yeah.
right? So they have some plugins do the point cluster. So click it and then it will boom. Then you can select any one of them.
Yeah, right now we don't have that sort of clustering in Lonboard. And so, like, what Lonboard tries to focus on is just like rendering as much data as it can, as efficiently as possible. And so you can zoom in, like instead of first showing the cluster and then the points, it'll just show all the points. And then you can zoom into a level that you can click on one of them. We want to also add like bounding box selection or some draw tools so that you can access, say, all of the points in this viewport and access those back in Python. Did that kind of answer your question?
Yeah, because you have the feature to get the selected index, right?
Yeah.
So it would be great to select overlapped points.
Yeah, right now we only select one. It's in progress to select some box of points. That just hasn't made it yet.
Hi, thanks for the interesting talk. I was just wondering, what is, in your view, like the current status of the integration of GeoParquet with traditional JavaScript libraries like OpenLayers, Mapbox? So how to directly visualize GeoParquet data through those libraries, and whether you're doing any work also at development seeds, similar to what you've done with T-Tiler and COG, for instance, to visualize tiles of these data sets.
I think that, so I've been focused on DecGL more than some other libraries because DecGL has a binary API where we can pass data without parsing it back into GeoJSON. If you are using smaller data, you could load GeoParquet to GeoJSON in JavaScript to pass into Mapbox or other libraries. Or you could try to do vector tiling of GeoParquet. I think this is the main technical approach that I've been focusing on so far, I guess.
Yeah, no, the question was that like when I work with this kind of data, I usually have a conversion step to PM tiles and then like you serve PM tiles through the web. So I was just wondering, like, it would be great to kind of avoid that kind of conversion and being able to stream essentially.
I think part of the question gets at, this is like way more performant than things that came before it, but it still renders all of the data without downsampling. And so it's not a silver bullet. Once you get beyond like 5 million points or so, depending on your GPU size, you'll still like, the map will lag and be slow. And so if you have like 50 million points, you can't use only this method directly. And so then it becomes a question of like, do you want the analytical data where here, if you're rendering polygons, this doesn't clip your polygons. You have access to the original full shapes in JavaScript and in Python. Whereas something like PM tiles, if you only care about the visualization, then it's really scalable. But you can't go from like one tile and say, what is the area of this polygon? Because you have to find what other tiles is that data in, and it's been kind of downsampled. And so not a silver bullet.
Thanks.
Okay, one short question from me. Does the GPU functionality require CUDA?
No,
Okay.
it uses WebGL. So
Okay.
any browser it works on essentially any browser, where even browsers without discrete GPUs will use some integrated or emulated GPU functionality, though it might be slower. But like on a recent Mac, this supports like 5 or 10 million points.
Thanks. So Lonboard looks really great in the notebook, but would it be something that you could use like in a Django website with like leaflet front end? Also bearing in mind that like it might be hosted on the cloud, which it's just on a VM that's CPU, not GPU. Would it be worth using for that sort of thing?
I think one of the like main focuses so far of Lonboard is exploratory data analysis, where like I actually have a page of the documentation that talks about this, where it talks about the internal architecture and talks about the goals and the target persona of Lonboard, of like Python user who doesn't know JavaScript and doesn't want to know JavaScript, wants fast exploratory data analysis, and your data's already in Python. And so this is using some other tools that can also be used in like pure JavaScript web apps. There is this HTML functionality. If I find, what did I call this map? So m.2html, geopython.html, open. Where here, this saved that data set. Oh, it even saved the view state. I didn't know it did that. To a pure HTML file that then this HTML file, you could give this HTML file to somebody else and they'd be able to see the same map. Now, that also means that the entire data is saved as a string inside the HTML file, base 64 encoded string. So this file is probably like 70 megabytes, but it does work.
It could be something that's useful to like show whilst other things like are loading, potentially.
Sorry, what?
That could if it's a pre-rendered HTML file, that could be something that's worth showing. Like if you pre-computed it.
Yeah, I mean here, like this still isn't like a pre-computed downsampled image. It is a like live static HTML web map, where this is, I don't know.
That wouldn't necessarily be any faster then. Okay.
So it's essentially the same as what you see in the notebook, just saved to a static HTML file that you can share with other people. But it's a big file because it stores the original data in the HTML file.
Okay, cool, thank you.
Okay, for other questions, please feel free to reach out to Kyle during the breaks. And I guess we have now a lunch break. So thanks, Kyle, for his talk. And see you in the afternoon.